my absolute pleasure to have Richard here as part of the day series, or the day prize of lectures from the National Academy of Sciences. And is this working? No? Well, I'll just talk louder. So Richard has won just about every award under the sun, including the Emiliani Prize, the, well, I have it written down here. Tyler Prize for Environmental Sciences, the Revell Medal, part of the AGU, the Siegelman Crystal, International Glaciological Society. He's a member of the National Academy as well as the Royal Society, and has served on the UN panels for climate change, among many other accomplishments. So I'm going to stop talking, and I'm going to let Richard take over. And so, Richard, thanks again for coming, and looking forward to this.
All right, cool. All right, thank you, Brent. Whee! All right, so pleasure to be here, old friends and new. So thank you, Brent. Do we, am I on? Are we coming through? Okay, we're good. Okay, so at any rate, thank you for coming out, and I hope to give you something to think about before we're done here. And so we'll see what we can do there. And for some reason, this was working fine, and now it's being persnickety. And so we'll see what we do. So thanks to Brent for inviting me and for organizing and for so much more. Thanks to you for coming out. And let's see what we can do. And also thanks to the National Academy of Sciences. I will bring them up later. So just hold for now. I'll show you where they fit into this story before we're done. Okay? So with that as sort of an introduction, let me start you out by going to Greenland. I have had the remarkable good fortune to go to Greenland on 9 occasions. If you ever get the chance, take it. Okay, it's really fun. It is a beautiful place. So this is the coast of Greenland, and you know it has Arctic hares in the winter plumage here, and you know it's a little. I hope you can see these, but these are musk oxen. You know this is a forest in Greenland. So with the musk oxen thundering across the way, and okay, so I used to go. I haven't been for a little while, but I used to go, and we'd get on these big transports. You'll notice that there's skis on the bottom of it, right about there. That's a ski. And we'd go up in the middle of Greenland, and once we got up in the middle of we'd get up in the middle, and you have trouble seeing this, but this is the middle of Greenland, okay? And you were 2 miles up in the atmosphere. You were on, you know, the nearest rock is 2 miles straight down because it's 2 miles of ice, or it's 200 miles that way. And we went up there to drill ice cores. And what you can barely see up here, this is actually a drill dome that a 100-foot tall drill is hanging on. And that's the midnight sun over it. Okay? And if you ever do get to go to Greenland, I'll let you appreciate this for just a moment. This is you'll see it's labeled A Good Day in Greenland. At the time I took this picture, we had been there for a month. And so the newspaper had come in a month ago. And it wasn't terribly current, but in fact it was perfectly functional. Now, as I said, this is a good day in Greenland. I will show you a bad day in Greenland, which is here. So it's the same thing. Okay. So in point of fact, and what we were doing in Greenland was drilling ice cores. And so here you have Kurt Cuffey, who's now a professor at Berkeley, looking at an ice core, and you have Wanda Kapsner, who is now up in Minnesota running a winery, but she is cutting ice cores. And we're in, talk about, for a dean or a department head, this is in our secret undersnow laboratory. And if we needed more space, we got a chainsaw, and we chopped out a bunch of blocks, and then we had a bigger lab. Okay, so this is a great place to do this work. And we're studying ice cores. I have a different talk. Someday you can get this if you need to. But we turn the ice cores into wiggly lines. And so here is a wiggly line plot. This 10 is 10,000 years ago. The 0 is up to today, and we run time this way. And the red one is how much it snowed, and the green one is temperature. We're just going to use the temperature one. And what you see is a very broad arch and some wiggles. And the very broad arch is features of Earth's orbit. It is, you know, the North Pole doesn't stick straight up. It's tipped over a little, and it goes a little more and a little less, and that's 41,000 years, and then a little more and a little less. And that moving of sunshine around on the planet affects temperatures, and that plus wiggle and some other things gives you this broad thing here. And writing on the back of that, you will see jumps. And those jumps are volcanoes blocking the sun and making it cooler. They are changes in the brightness of the sun. They are maybe changes in ocean circulation and some other things. And this is just temperature in Greenland, but it looks like temperature around much of the North Atlantic region. And the size of the changes is sort of a degree or something like that. And the last couple here have names. And they have names because they were big enough that they mattered to people. And so you'll see medieval warm period and little ice age up there because that actually was something that mattered. Okay? Now, when you get to Greenland, if you ever do, if you get a chance to go down here to Volsey, you remember that Greenland is settled by Vikings. Iceland is green, Greenland is icy. It was always an advertising campaign. But if you get a chance to go down there, you can go visit the Cathedral at Volsey. And it's one of the more beautiful things. It's a little two-story stone church sitting on the side of the fjord. And they built this in the 1300s. The last known use of it, you see noted right up there, September 14, 1408, there was a wedding here. And people had sailed over from Iceland, they witnessed the wedding, they went back to Iceland, and they wrote about it. And right after that, they abandoned this place, and now it's just this beautiful church sitting there on the side of the fjord. They settled Greenland in this medieval warm period, when it was a little warmer and a little greener there. You'll recall that most of the world is the big band around the middle where there's a lot of people and it's a little hotter than comfortable. A little of the world is the cold caps, like this, where it's a little colder than comfortable. And this is one of those places that is a little more comfortable when it gets a little warmer. And so people settled here in the medieval warm period, and then as the little ice age came in, the native people, the Thule Inuit, stayed, but the Vikings, you know, it's hard for the bishop to get to the church because the ocean is freezing, and eventually they just gave up. They became environmental refugees, and they left. And so this little wiggle right here was enough to affect people living on the edge. Now, I emphasize that because you'll notice I left this out, okay? And so this is real. This is Greenland. But that change right there is about 10 Celsius or 18 Fahrenheit in about a decade. It's not a CO2 signal. It's not the whole world getting warmer, but it's a circulation signal. So some places got warmer, and some got colder, and some got wetter, and some got drier. But pretty much everyone on the planet saw a climate change that mattered to them. And we can talk later about what this is. It's sea ice and ocean circulation and some other things. But this was sort of, if this matters to people, this is a big deal. Okay? Now, this is just 18,000 years. If I take a little longer view, which I can do, this is the last 100,000 years. The previous slide is this little box over here, and what you'll see is sort of craziness, and then it gets a little bit boring up there. And so this thing is going, whoop, boring, okay? And what happens right there at the boring corner, pretty much everywhere around the world, people start growing plants on purpose. It's the origin of agriculture. And you see it in China, and you see it in the Middle East, and you see it in the Americas. As soon as the world got boring enough, people go to agriculture. So let me zoom back in over here, and we'll do something here. Right? So here is the crazy world of the Ice Age. Here is the not quite so crazy world that we live in now. And there's a corner right there. Now be clear. I will later tell you CO2 is a greenhouse gas. CO2 is a greenhouse gas. If you want to argue about that, you should go home and look in the mirror for a very long time. Okay? I'm going to tell you a story about people across this. I will guarantee you that this is not the complete story. People are never as simple as anything I can tell you in one story. I cannot do proper justice to all the motivations of people. But what I'm telling you, I believe is accurate, and it leads us somewhere which I hope is useful. So remember that as we go. And so let's ask the following question. What is life like for a hunter-gatherer in the Ice Age in a good year? You're grown up, things are okay, you got your health, and so what is life like over here when it's good versus what is life like over here when it's good? And so we'll see what we can do with that. Hunter-gatherers on one side, farmers on the other side. And what do? Right? On this side, you like it here, yeah, it's fine. You get tired of here, you go there. What do you do over here? You spend all summer scratching the dirt with a stick. Right? Anyone who has hoed a lot, this is not as much fun as this. Okay? There's no one in this room that has to hoe corn all summer so you don't starve to death that winter. But that's a pretty rough way to go, and with a modern hoe, it's a lot easier than with a digging stick of some sort. And what do you eat if you're a hunter-gatherer? That's what they keep trying to get us to eat. It's the whole food pyramid. What do you eat if you're a farmer? Maybe there's a little milk, and when the cow gets old, maybe you eat the cow, but otherwise you grow grain and you grind it up. I mean, it's gruel. And, and this is probably the biggest one, is the one that comes next, which is, one more. So, you get a bug. You go behind the tree, you leave your duty, you come back in a year, your bug is dead. You get a bug, right? If you were a sophisticated early agrarian, you were pooping in somebody else's drinking water. If you were not sophisticated, you were pooping in your own drinking water. And there really isn't a third choice. And so what do? You settle down with your diseases, and they know where you are now. Okay? And so what you end up with is a switch from the hunter-gatherers in good times. They're big, they're strong, they got good bones, they got good teeth, things are okay. And you switch to all sorts of nastiness as you go across this boundary. And yet, everywhere around the world, as soon as they could, they did. And that's a fascinating question. Why would you give up this to get this? And everybody did it. And I can tell you that you will get lots of different answers from lots of different disciplines in the academy. But it's moderately clear that at least part of the story is here. Which is not only was the world full, it was probably overpopulated with hunter-gatherers. If you have a bad year, and the drought hits your valley, and there's nothing to hunt and gather, and you want to go into the next valley, you can't do it, because there's somebody there and they want your valley. And it's pretty clear that if you have a drought when you're limited in your range, what do? Your kids and your grandparents die. And that's probably it. And as our ancestors spread around the world in the late Ice Age, they were causing mass extinctions, contributing to. They were contributing to reduction in the carrying capacity. They get to the Americas, and what do they see? Stakes on the hoof. And then they sort of are all gone. And so it's fairly clear that with probably a few million, maybe a few tens of millions, but probably just a few million people, and the technology they had, that the world was overpopulated. And they switched to doing something else to bring more food into existence so they can feed their families. And so we go from a world that's overpopulated with a few million to a world which may or may not be overpopulated with a few billion. And this is an interesting thing. Without our know-how, without our technologies and our know-how, of the next 1,000 people you meet, maybe one survives. That's sort of a big number there. Okay? And so this business that we've actually learned to beat this thing. And we've gone from, let's face it, drinking our diseases and eating gruel to what we have now. And I'm not sure what we're going to get for the reception, but I'll bet you it's better than drinking your diseases and eating gruel. Okay? And so it's truly amazing, but it's based on learning and building and growing and sharing and teaching. And those are very clear. And I don't even have my cell phone in my pocket. It's probably over here someplace, right? You probably have one of these. It's a fascinating thing to do if you've ever tried this, right? You go visit a 5th grade class or something like this. Say, what is this? And they, oh, it's a cell phone, or it's your phone. Or they say, wow, that's sort of an old little one, isn't it? And you say, what's it made of? Cell phone parts? What's it made of? It's a handful of sand for the glass and the silicon, and it's a little bit of oil for the plastic, and it's the right rocks, the ones with the copper and the rare earth elements and what have you. Right? This is sand, oil, and rocks. And science and engineering and a little design and marketing. And I can guarantee you, if you took the sand and oil and rocks and gave them to various groups, the U.S. Senate, or the football team, and you said, please turn that into a cell phone, I can guarantee you that you would be waiting a very, very long time for that. Right? This is just truly fantastic. And you know, Einstein is in there. He uses relativity so it doesn't get lost. And you know, Bohr and Feynman are in there. He uses quantum mechanics in the computer. And yet we do have lots of people who will take their cell phone and send us a note that says, you scientists don't know what you're talking about. Right? Irony is not lost, okay? Be very interesting, okay? So be very clear. What we've developed, what we've built, we love this. And it is not optional. Knowledge is not optional. Learning is not optional. Tulane is not optional. Okay, you're required. And you know, we have to get along with our neighbors. We have to clean up after ourselves. And so, you know, this business of learning what happens and using it is the best thing we've ever come up with. And it's why there's so many of us here who are going to have a good dinner. You know, this is something. So you know, ultimately you may have a sustainability institute. Most people do sustainability somewhere in their university. And so let's think a little bit about this. A lot of what we worry about is how do we live so we keep us alive and our kids alive and our grandkids alive and our grandparents alive and our grandkids can do the same. Right? How do we keep things running like this? The UN's looked at this and they said there's a bunch of issues that we should solve. Agriculture is big, water is big. Probably energy is the biggest one because so much of agriculture and water are also linked to energy. And so ultimately, you know, you walk through, I'm going to focus on energy and climate. Recognize that phosphorus and agriculture and water are really big. But of the technical issues, what do we have to figure out to make the future work? Energy is certainly right near the top. Probably the biggest one is getting along with each other, but solving the technical ones makes that easier. Okay? So we'll do this. Right? U.S. diet is probably a little over 2,000 calories per person per day, but it's something like this. What we can do for ourselves, right, is 2,000 calories per person per day. But that doesn't provide the lights, and that doesn't get me here from State College and back to Pennsylvania, and that doesn't cook the food, and that doesn't plow, and that doesn't do a whole bunch of other things. If you take total energy use in the U.S. economy, divide it by the number of people, convert it to these archaic units, it is 240,000 calories per person per day. You can do 2, you get 240. And as each of us has more than 100 energy serfs to do our business. And we love it. Don't kid anybody. I am not walking home. Okay? Don't, right? And it's right now it's about 85% fossil fuel. So that's it's a great thing, you know, and like I say, we really love it. But we have this long history, which I'm going to show you a little of burning some energy source far faster than nature makes more, running into a crisis when it becomes scarce, dealing with the unintended consequences of that use, and then trying to find something else, often when the shortage hits with very intrusive governments and lots of laws and other sorts of problems. So we have this long history of, we're farmers of food, but we're still hunter-gatherers of energy. And so let's walk through a little of this story. I came down to you from central Pennsylvania. My university was founded not next to a city, not in a city. It was founded next to the iron furnace. The town that I call home did not exist when my university was founded. We were founded next to the iron furnace. And the iron furnace, when it was working, might have looked something like this. It was turning red dirt, iron ore, and a little limestone flux, and charcoal into pig iron, and the east was built of Juniata iron. And when this thing was running, there were probably 100 people living near it that were attached to it in some fashion. So it was a whole little city to make the iron furnace work. And the iron furnace was charcoal fueled. And so they would cut trees. This is late in charcoal making. This is just as it was being forgotten. Somebody went out and filmed someone making some to see how it was done. But you'd make a big pile of trees. You would cover it with dirt. And then you would burn it with restricted airflow so that it wouldn't burn up completely. And if this is not yet covered with dirt, and so they're on it getting ready, but once it's covered with dirt, if the dirt broke, you have to go up and patch it before your charcoal burns away. And that would be really bad, because if you fell through, that was the end of it. But what did it do? This. A furnace in blast took more than half a square mile of trees per year. And it had 100 people who were building houses and cooking and heating and other things. So you can figure a furnace was a square mile of trees per year. If you go to a map of Pennsylvania today and you ask how many places still have furnace on the map, it's here. Each of these, when it was in blast, was a square mile of trees a year. And then they shipped them to forges like Valley Forge and a bunch of other forges, another square mile of trees a year. And what happened is the trees were gone very, very quickly. And so the first forester of the Commonwealth of Pennsylvania was a fellow named Rothrock. He had been a professor at my school. He talked about the Great Pennsylvania Desert. Now, it wasn't a desert, but it was treeless. We have 1 million deer in Pennsylvania now. There were essentially no deer. We're the Nittany lions. There's no Nittany lions. There wasn't a tree to do it behind, and there wasn't anything to eat. And so we just flattened the East. And it wasn't just Pennsylvania. The whole East. In the 1600s yet, Eastham in Massachusetts on Cape Cod outlawed your ability to cut your own tree on your own property because deforestation was so extreme. The government came and got in your face because they were really worried about what was happening. The whole East was just cleaned off, basically. Now, if you've ever tried to read by firelight, it doesn't work very well. You can try candles. They're not much better. 12 stitches to the inch on a quilt, that's difficult, right? And poor people used to use something they called camphene for lamp oil. It was a biofuel. It was a mixture of alcohol and turpentine. It was cheap. It had a clean flame. But it was really flammable. They sort of blow up. And you can find these horrible stories. You know, the Methodist minister and his wife go out to visit the parishioners, and the 3 daughters try to refill the lamp, and they burn themselves to death. And the rich people used to burn whales, or whale oil. And you'd send Yankee sailors out to scour the world ocean for all the whales that you could find, and you'd cook them, and you'd turn them into whale oil. And it was clean, and it didn't stink, and it didn't blow up, and it burned well. And so this is the history of whale oil production in the Yankee fleet. 1800 is over here. 1880 is over here. You can see peak whale oil up there. Okay. This is a complicated curve. There's a civil war in there. There's the fleet being crushed in the sea ice off of Alaska and the insurance price going through the roof. But what was the fleet doing in the sea ice off of Alaska? They couldn't find whales they could catch closer to home. And so at the peak right here, there are 10,000 sailors out of New England scouring the world ocean for whales. Up here's the price. In modern money, it got down to $7 a gallon. And when they hit peak whale oil, it went up to 23 in modern money. And right after that, they went right up the road from where I live, and they drilled the first modern oil well. Oil was leaking out of the ground, and they said, wow, there's oil in the ground, we'll drill here. Okay. 10,000 sailors, 100 years of Yankee whaling, and, you know, 5 years ago, it was sort of a week of U.S. oil imports. The idea that somehow when we run out of fossil fuel, we go back to what we used to do is completely laughably absurd. There's not a chance in heck. Okay? 100 years of whaling for a week of imports. You know, it just doesn't work. But we have whales and trees now because we burn fossil trees and fossil algae. And it's really about that simple. We have whales and trees because we burn fossil trees and fossil algae. And they knew it way back then. So here we're gonna I'll pop this up here. There we go. Okay. This is an editorial cartoon, was published in the magazine Vanity Fair in the year 1861. Okay. This is just before the Civil War. And this is the grand ball given by the whales in honor of the oil wells of Pennsylvania. And you can find up here, oil's well that ends well. The oil wells of our native land, may they never secede. We wail no more for our blubber. We have whales because we switched to burning oil. Okay? So we like that. It's really good. We like whales. Most of us anyway. I do. Okay? And this has to end. The oil that we're burning accumulated over a few 100 million years. We are burning it over a few 100 years. We are burning it something like 1,000,000 times faster than nature saved it for us. And so it's not a question, do we build a renewable energy system? It's only a question, do we burn the fossil fuels and then build the renewable energy system, or do we get started on it earlier? Because there's just no way that this changes. How good the oil companies are and the coal companies at giving us what we ask for is flabbergasting. What we put out in the trash can at the curb for the trash collector in the U.S. is a little under 1,000 pounds per person per year. The CO2 that we put in the air from our fossil fuel burning is about 40,000 pounds per person per year. 1,000 at the curb, 40 in the air. If we took the CO2 and we liquefied it, or we made horse ploppies and we put it on the roads, it would be 1 inch deep in a year for every road in America. In a decade, there would be no joggers in America. We would all be cross-country skiers, and we would not be having this discussion. Okay? First modern oil well, they drilled it where oil was leaking out of the ground. What is BP doing out in the deep water of the Gulf? The easy stuff is already gone. Okay? But there's a whole lot of fracking to be done. There's a whole lot of mountaintops that have not yet been taken off. If we do the hard stuff, we can burn a lot more. But it's only buying time. This will end. It's not if, it's when. Okay? And that brings us to this one. That 40,000 pounds of CO2 per person per year in the U.S. is going into the air. And that matters. And we have known that for well over a century. It was refined by the Air Force right after World War II. Okay? They were not doing global warming. One of the jobs of the Air Force after World War II was to make sure that bad guys with bombers didn't blow up our cities. One way you can cure that, that's a picture of a heat-seeking missile. An enemy bomber has a hot engine. The hot engine emits infrared radiation. You can follow that radiation up his tailpipe and make sure he does not get to your city. But if you put the wrong sensor on, you can't see the target, because CO2 or water vapor in the air soaks up that infrared radiation. It transfers it to the other air molecules in collisions, and rather than seeing a hot spot, it just sort of warms the whole air. Now, if you were outside walking over here, the sun warmed the Earth. The Earth is sending infrared radiation to space, and CO2 is blocking some of that. And that's this plot over here, right over my head. This is the Earth cooling off, as observed from satellite. And this is CO2 blocking some of that. And if there were more CO2 in the air, it could block more. And it's really this simple. This is observed reality. There is more energy going up out there right now from the sun-warmed Earth than coming down from enemy bombers. And CO2 absorbs some of that and transfers it to the other molecules in the air to heat the whole atmosphere. And as we raise CO2, it can do more of that. And it's really sort of people, you know, you get to this point of saying, why do you believe in global warming? We don't believe in global warming. Global warming arises from unavoidable physics. And this is just about as solid as, you know, if I drop this, it'll fall down. If there's things about gravity we don't understand, but basically you put CO2 in the air, that is radiatively active. We don't know what to do with that. This one may be very important right here. You can't call somebody in to hear the other side. There is not another side. Science is the best we have. There are people who think I am being too alarmist in what comes next. There are people who don't think I'm being alarmist enough. But there's not another side. This is reality as we know it. Now, I'll mention the National Academy. I will guarantee you that you could find a scientist who would come in here and argue with me. We could find somebody that would argue about Einstein. We could find somebody that would argue about evolution. We could find somebody that would argue about plate tectonics, for goodness sakes. You can always find, and we sort of celebrate this, because the best idea in science is the one that has survived the most attacks. And so at some level, we desperately want people to argue about this. And so there's always been this problem that we as scientists like, bring it on. Okay? But policymakers need advice. And so at some point, policymakers have said, what do we do about this? How do we lift the lid on science, pull out what we want, slam the lid back down, and let them go about doing what they want? And so back during the Civil War, the House, the Senate, Lincoln, on the same day passed the bill, says, let's get the National Academy of Science as advisors to the nation on matters scientific. We will get the best scientists acting in the public eye for the public good to tell us what's solid, what's speculative, and what's silly. Okay? They just put them to work right away. If you remember the Battle of the Monitor and the Merrimack, by the time the ironclads got done fighting, every navy in the world, as soon as they heard about this, started putting giant slabs of metal on the sides of their boats because it worked. And you have a magnetic compass, and you just put giant slabs of metal next to it. Which way is north? And so the nation goes to the academy and says, there's various people telling us various things about how to fix our compasses. What do we do? And the academy fixed them. Okay? And the North navigated through the rest of the war knowing which way north was. And this is a good thing. Okay? So for what it's worth, you get the full range of scientists. You get them to act for the public, in the public eye. And now it is the National Academy of Sciences, National Academy of Engineering, the National Academy of Medicine, advisors to the nation. And this is where you start, for what it's worth. There actually is a Water Science and Technology Board. And if you want to see reducing coast risks of the Eastern Gulf Coast, for example, you can go look there. Okay, if you're serious about this, one scientist does not speak for science. You'll always find somebody to argue. You go look at the assessments if you want a good starting point. Okay? So, back to climate, back to energy. Okay, I wrote a book on this. I made 3 hours of PBS TV. We ran a MOOC. We do a Penn State MOOC. I've got chapter and verse if you want it. But the skinny version, yes, fossil fuel burning is raising CO2. This is having a warming influence. The world is warming. And the world is warming despite the fact that over the last 30 years the sun has dimmed a little. In some places we have replaced dark forest by more reflective grasslands, and volcanoes have blocked a little bit of the sun, and we have blocked a little bit of the sun of the particles. Best estimate, how much of the warming that is occurring has been caused by greenhouse gases? More than all of it, because these other influences have tried to cool. You will meet someone who says, oh yeah, I know it's getting warmer, but isn't it natural? No, nature tried to cool it off, and still it got warmer. So how much is ours? More than all of it, really. The warming has the size, it has the pattern we expected. It is doing what was projected 30 years ago, almost. And this confirms our understanding, and that says that if we keep doing what we're doing, the changes will get a lot bigger. Okay? This is the bottom line of what the Academy says, it's what the Royal Society says, it's the IPCC and so on. Nobody cares. Right? Big whoop. Right? We care more about this. What does it mean for us? What does it mean for other living things? And there's a bunch of these sea level rise matters around here. Grain belt drying. I'll show you a little of this. If you want to talk about crop heat stress, we can come back to that later. It could get too hot to grow a lot of our food. A lot of our food is grown at temperatures a little warmer than it likes already. You're trying to save rare and endangered species in your national parks, and now they need to move 1,000 miles, and there's wheat fields in the way. What do you do? You know, there's a big storm hitting Mexico about now. It's fairly clear that there's more fuel. We may not get more hurricanes, but the biggest ones can get bigger in a warmer world. This one may drive people crazy, more floods and more droughts. But all winter, my tomato patch is damp or frozen. In the summer, we get a gully washer, and 2 weeks later, I'm watering it. Right? You get more variability in a warmer world. We make the world warmer. We get more variability. We actually get more floods and more droughts with fairly high confidence. And the biggest one, and we'll hit this again, a little bit of warming doesn't cost much. As the temperature goes up, the costs go up faster. And that's important. Okay? So let me walk you through this. This paper came out this summer in the Proceedings of the National Academy of Sciences of the U.S. If I zoom in on a couple of keywords, Syria was not a happy place a few years ago, but it was a lot happier than it is now. And they had a drought, and they pumped a lot of water out of the ground to try to keep the crops going, and then the food sort of ran out, and the price of food went up, and then bad things happened. And it's fairly clear that our changes to the climate already made this drought more likely. We loaded the dice to come up drought, and a drought hit. Okay, now that's just one paper, but there's some other stuff that points in the same way. I'll show you in a minute. This is a different paper. Again, this is just one, but there's other stuff that points in the same way. And this is a projection. If we keep burning, but not too fast, by the time our students are starting to get old, what happens to drought? And on this plot, green or blue is less drought. And you can sort of see way up there where nobody much lives now, there's a little less drought. But if you look at the places where a whole lot of people live now, what do you see? More drought. And in particular, if you zoom in on the place where we already have an idea that drought is causing nasty things, red is more drought. Okay, so we're already pushing them in a way that makes them fairly unhappy. And the projection is it gets a lot worse. Okay? Now, this has not been passed the notice of people who matter. So the CNA Military Advisory Board, this is retired generals, retired admirals, and what have you. And they said, okay, look. It's down here at the bottom. Climate change did not cause the conflict. It certainly added environmental stressors. If you're unhappy, if things are not working very well, if you're having troubles feeding your kids and your grandparents, and then the climate changes in ways that make it harder to feed your kids and your grandparents, you get unhappy. And they traced the dashed line, or the dotted line, that leads from drought to civil war in Syria to, drought and heat and so on. It's fairly clear that the little warming we've caused so far is starting to have impacts. Now, you can't easily trace one event to human cause, but we load the dice. We make things more likely, and then they come up. Okay? This is an interesting thing. I was at Duquesne University recently talking to a conference on the integrity of creation, and this comes up. Per person emissions of CO2, red is high, blue is low. Who is changing the climate today? Rich people in cold places. Who is not changing the climate today nearly as much? Poor people in hot places. Who is vulnerable to the changes? Right? If we have winter bulldozers and air conditions, a little warming doesn't hurt much. If you don't have bulldozers to make walls against the rising sea, you don't have air conditioners so you can work when it's hot, you don't have winter to lose when it gets warmer, you don't gain from heat, it hurts you. This is who's most vulnerable to changing climate in red and who's not very vulnerable in blue. So red is changing the climate and red is hurting from the changes. Okay, now, if you believe in the golden rule, that's an issue. And so if you caught it, the Pope says, it's clear to me that climate change is a problem which can no longer be left to a future generation. Okay, Duquesne was interested in that. All right. And just in case you want to bring it home, here is a projection from a different study for drought in the U.S. as we run into the future. And yeah, up here is not getting more drought, but, you know. Okay, right. And then we come back to this one. We've always lived with variability. 1 degree of warming, what's the big deal? We've had 1 degree of warming. So far, it's starting to show up with impacts, but it hasn't been huge. We're still here. We're still doing okay. Sea level rises a little bit, but, you know, the sinking of the delta is probably more important than the rising of the sea so far. The 2nd degree of warming starts to move you out of your comfort zone, what you've dealt with before. We're already committed to that with fairly high confidence. And remember, this is degrees Celsius globally averaged. Land warms more than the ocean, and Fahrenheit's more than Celsius. So you're starting to talk about arguing about 3, 4, 5 Celsius. You're arguing about, you know, 5, 10 or more Fahrenheit on land. And that's what we're discussing now is the 3rd, the 4th, the 5th degrees. Okay? So you start to get to the point, if it gets hot here, and whatever it is you've grown doesn't like it because it's too hot, there's somebody living in a hotter place and you borrow something from them. But what happens when it gets hotter than anywhere on the planet now? What do you borrow now? And so we've used the cheap degrees, and we're talking about the expensive degrees right now. And the worst case scenarios, you know, not in our lifetime, but the worst case scenarios are things like it's too hot to live in the tropics, which would be a big deal. Okay? This is also important. You'll routinely meet people who say, well, we're not sure. Shouldn't we wait till we're sure? Okay, but you think about this a little bit. Building takes getting a lot of things right. Breaking is a lot easier. If you tried to build a cell phone, you can't do that with a hammer, but you can break it with a hammer. If you try to build this building, you can't do that with just a hammer, but you can break it with a hammer. And so you think about cranking up CO2. Can you make Eden by just cranking up CO2? Probably not. Could you break something you care about? Possibly. CO2 is plant food. It helps them grow. That's been included in our assessments for a very long time, and it seems to be working. Plants like that. But they can't grow a lot better with just CO2 because they also care about water and temperature and frost and pollinators and bugs. But if you make it too hot or too cold or too wet or too dry or give them too much fertilizer or too little fertilizer, they can die. And if their pollinators don't come at the right time or invasive species come and eat them up, they can die. And so you expect plants to grow a little better with CO2, and they may even do a little better than that, and they may do a little worse, or they may die. And so the uncertainties across the board, I talked about sea level rise to some people in the department this afternoon. The uncertainties there are the same thing. We have an expectation. It may be a little less, it may be a little more, it may be a lot more. And so what we don't know, it could be really bad. And the uncertainties are heavily weighted on the bad side. Good research may cut off those long tails. We hope it does. But for now, you know, the lack of knowledge is sort of a reason to be more worried about this, not less. And that's good common sense. Okay. Now, if we had more time, we'd walk through the economics, we'd walk through the policies and a whole bunch of things. But it is actually the summary result of all these assessments is that releasing CO2 to the air has a cost to society which is not reflected in the price. And that if that were reflected in the price, society would be better off economically. if you care about money, across a great range of studies, using this knowledge wisely makes us better off than pretending it's not real. It's dollars and cents, it's jobs. If you care about rare and endangered species, or taking out insurance against disasters, or national security, or the golden rule, then you would probably do more now to slow down global warming. But the economics are, the economy of the world is better off to deal with this. Okay. Then we come to the last little bit, and then I'll shut up. The question of, so suppose we decided to do this, is it doable? And the answer is unequivocal on this. Yes, it is. This is very, very clear across a huge number of studies. Okay? So let me do it this way. This is where our food comes from. The top picture is croplands. The redder it is, or the oranger it is, the more of the area is used for food. And so up here is the areas that we have changed to grow our crops. There are places that things grow that we can't eat, but animals can eat, and we can eat the animals. And so down below is grazing lands. And so to get our 2,000 calories per person per day, we have changed the land across those areas. Now suppose that we decided, with modern technology, to build a solar farm that would supply more energy than we now use. And we decided for the moment, just for illustration, to put it out in the Sahara. You would never do this, but for illustration, let's do this. How much area would we have to change to supply more energy than we now use with existing technologies? And it's right there. Okay, now no one will do that. And be very clear, that is a lot of solar cells. This would not be easy. This would be decades. But just in terms of a scaling, we have learned how to get food off of all of that, and that much area of solar cells would do the job. Okay. Now, this one's great. Before he's elected president, Abe Lincoln is running around giving speeches on learning and patents and engineering and science and so on. And one of the things he says is the wind is an untamed and unharnessed force, and one of the greatest discoveries to be made will be the taming and harnessing of it. Okay? And if we built a wind farm with existing technology on the windy parts of the plains and deserts of the world, not in the forests, not in the cities, not in the water, not on the ice, the windy parts of the plains and deserts of the world, that is far more energy than we now use. Okay? Now, we filmed some of this stuff for our TV shows. And, a rancher puts 5% of the land into wind turbines. A wind turbine pays $5,000 or more per year to the rancher. They call it mailbox money. You go out to the mailbox and you get money out of it. And this actually pays a whole lot better than these do for a very small fraction of the area. And so a lot of these Texas ranchers who didn't much believe in climate change really believed in wind. Okay? So go back. When we switched to farming food, it took us thousands of years to figure out how to do it. But we're better off we're here because we did. Learning how to build a sustainable energy system is not going to be instant, but it's 30 years. It's not thousands. Because the technologies are already there. We remain hunter-gatherers of energy, but we now know, and we're the first generation in history that knows how to do this. And we have high confidence from a whole lot of scholarship that not only does doing it help the golden rule, but it helps the economy. And that's sort of an amazing thing, and it's a very optimistic thing in some sense. And so let me leave you with maybe my favorite picture, which you can just see here. This is an iceberg, and that's a rainbow. I took this up in Greenland once. Can we have a world with icebergs and rainbows? Absolutely. Thank you. Now, I hope we have time for questions. We did not succeed in making a mic work, but if you yell, I'll repeat it if anyone can't hear it, and I will very happily take questions. Yes?
What's your assessment of how close we are to tipping point? I mean, if we're
Yes. So this is the tipping point. Probably most of you know what he's talking about. You know, if I balanced my pen on a table like this and I bumped it a tiny bit, it would stay there, and if I bumped it a little more, it would fall over. And that would be a tipping point. And we're very nervous. Those changes in the North Atlantic were tipping points. We don't think one of those is going to hit us fast, but there's some changes going on that are just a little disquieting. I talked this afternoon about collapse of the West Antarctic ice sheet. That very clearly is a system that you push it a little bit more, and at some point it tips, and it's really bad. You make it too dry in a big piece of forest, and it burns, and the forest doesn't come back, and you've got a new ecosystem. And it may not be nearly as nice an ecosystem as the one we had. Syria. At some point, you tip over the social issue, and oh my goodness, what happens? And so the worry that we will hit these tipping points is real. Probably, it's still averaged over humanity. Dealing with this is still a little bit like saving for retirement. All delay is costly. Every minute you delay is costing you money. But whenever you decide to start helps. And that's probably the best way to look at it. It's all delay is costly, but whenever you decide to start will help. It's not a case that all of a sudden we lost West Antarctica and we're doomed. Okay? Some cities may be in trouble. Some coastal regions may be in trouble, but Greenland's still there and you can try to save that. And because the costs go up faster than the sea does, if you actually are committed to losing West Antarctica, saving Greenland is now worth more. I can do the math for that if you want, but it's a fascinating thing that because costs go up faster, if you tip anything, if you start belching out methane and it's cranking up temperature faster, reducing our CO2 is worth even more. Yes? Right. So the question was a gas which is counter greenhouse gas. I haven't read this one, and I don't know what it would be. It is very clear that when we burn fossil fuels, or when we burn biomass in crude stoves in the third world, that not only do we put up CO2, but we also put up particles. And many of those particles block the sun. And so you get a warming from the CO2, but you get a little cooling back from the particles. And the truth is that cleaning up the fossil fuels, we'll see a little more of the warming we've already caused because you'll pull the particles down. But it's fairly clear also that the health benefits of that are really big. So I've actually seen there's a few studies that have looked at the impacts of coal. And as we implement it in the U.S. And coal puts up CO2, but coal also puts up particles that people breathe, and it puts up acid rain and a few other things. And the studies, and I can find you chapter and verse on this, the studies that have been published on this in the refereed literature that I know tend to indicate that the cost of the health damages from breathing what comes out of a coal plant are higher than the cost of the electricity. So you pay 9 cents a kilowatt hour or whatever it is for the electricity, and the damages to society of breathing what comes out with it are more than that. They're 15 or something like that. And the numbers go up to $1 for some plants in one study. So it's fairly clear that even though pulling those particles out will have a little bit of a warming influence in the short term, that by getting them out of our lungs, that's actually beneficial. Yes?
Solar and wind has been growing at 25 to 50% per year, just following the long law of learning for now almost 3 decades. And they've just been up against the fact that our electricity use is up at 10 to 12 watts. And in another about 2 decades, there's this transition, and that's why people in utility companies are so nervous because their whole business model has to change far quicker than their plans do. So I'm actually not worried about that because that transition is going to happen, and we can make it the energy economy to a sustainable, carbon-free thing, there's still this large pig moving through the python, right? So I'm interested, as someone who's clearly thinking on the timescale of centuries, what's the problems we should be thinking about scientifically about how do we kind of prepare things on the far end? Because the energy transition is going to happen.
Okay, so if you didn't catch it, he's optimistic the energy transition will happen without much action.
Well, no, I mean, we're all working, but it's going to
Yes. Okay. I hope that you're right, since we don't seem to be acting really strongly at this point. I suspect that with the laws can probably move that transition by more than a small number of years. So you said 2 or 3 years to move the transition. I suspect that if somebody said, no, you can't sell solar back to the utility anywhere in the U.S., and we're not going to allow you to do that, that you would move it back decades and not years. So we can talk about this later, but it's a very optimistic view to say that with no policy action from any of us, that it will only affect things by a couple of years. And I think you'd have troubles finding widespread agreement on that yet. Okay. The question of, so we put the CO2 up. And so what does it mean? And, you know, once we raise CO2 in the atmosphere a lot, it takes a long time to come down. And initially, what happens, we add more CO2 to the air, and more of it goes into plants, and a whole lot more of it goes into the ocean. And recently, almost half of what we put up has been going somewhere. The more we put up, the harder it is to put it rapidly in those other places. And the long term is that it takes 100,000 to 500,000 years to get rid of all we do. So eventually what you do, you put it up and it goes in the ocean and it starts dissolving shells in the seafloor and coral reefs or whatever you have. And then eventually you have to wait for it to break down volcanic rocks or other rocks and make raw materials for shells and regrow those shells and run them down the subduction zone. And so the time scale that we will perturb the world once we put this extra dollop of CO2 in is long. And it gets longer the more we put up. So there are many people looking for options. Can we make the reaction with the rocks go faster? Can we take it out of the air and put it in the ground somehow? And really bright ideas floating around about this. I'm on record as cheering for the research. I'm not hugely optimistic that we're going to do a lot of it. I think there's strong issues that come up. You start pumping it in the ground here in Pennsylvania, there's a whole lot of holes that we don't know where they are, and you pump it down here and it comes spouting out over there. And so there are issues that could be solved. They're all technical, but whether we'll pay enough to solve them is an interesting thing. And then, you know, I mean, there's a paper came out about a week or two ago that said if we burn it all and make it warm, it's enough to melt all of Antarctica. And all of Antarctica plus Greenland plus the mountain glaciers is now 200 feet of sea level. And it's not happening in anybody's lifetime here. It's millennia, it's not centuries. But if you start thinking about going straight up 200 feet, you know, Florida's. So it becomes a really big long-term thing. There are also people who have looked at this idea, well, why don't we just block the sun with more particles? The particles work, the volcanoes work, we're blocking the sun with particles, let's block the sun with particles. And it's pretty clear that you could fly 747s around at the edge of the stratosphere belching out sulfur dioxide that would make little particles that would block the sun. And there's a bunch of issues about, you know, a little acid rain and some ozone destruction, and it's not just anti-CO2, and so you cause a lot of droughts. But there's also, you have just committed people to 10,000 years of flying around. So, and more. You're looking at doing this for a longer time than civilization has existed. And so, yeah, there's people doing the research on that, and there are people who glibly say, oh, we'll just block the sun, don't worry. But, you know, those also tend to be people who would be very upset if the UN told them what to do. But this would sort of be a global effort. So yeah. So we're doing something that would be very, very long-lasting. And at time scales that dwarf the history of civilization if we burn it all. Yes. So. Yes. Yeah, so the one so if you did not hear, this question of attributing, is this hurricane caused by global warming? And it's very, very hard to take one event and say that was caused by it. And the analogy, let me walk through the analogy, and you know this already, but we'll do the analogy anyway first, which is suppose you're playing Yahtzee with somebody, you're playing some dice game, and they roll sixes. And then they roll sixes again. And then they roll sixes again. And then you look at the dice, and the corners are filed off, and there's a little lead in one side. You know? And you can't prove that rounding off the corners and loading the dice caused the sixes to come up. Because it is possible to roll sixes with fair dice. But you know which way it's biased. You made it more likely, and it happened. And so some things now, sort of the science of attribution, you do a lot of work, often with model experiments, and you say, okay, if we run centuries and centuries of the climate for this particular place under pre-industrial conditions, we get a heat wave this often. We get a storm this big this often, whatever it is. Now we do it with the change conditions, and we get it 3 to 4 times more likely, or 2 to 3, whatever it was on that one case, and pretty soon it's 10, and pretty soon it's 100 times more likely, and then you say, okay, so we can't prove this couldn't have happened without us, but we made it far more likely and it happened. And so at that point, I think most people, as you make it much more likely, most people would say, yeah, we share the blame for that. We're seeing more of those events. Naturally, we understand why we're seeing more of those events. Our models of various types run in various ways by various groups tell us we should be seeing more of those events that are occurring more rapidly. And you say, okay, we did that. Then there's been a little bit of bubbling at this point. I'm not an expert on this. Okay, but there has been a little bit of bubbling in the edge of the mainstream press and out in the greener press. We know that tobacco companies got themselves into trouble at some point relative to public statements that had been made that were not consistent with what they knew internally about the role of tobacco in causation of cancer. And there are reports out in fairly good press that certain oil companies who funded efforts to confuse science or to funded efforts that would have given you a very different talk than this actually knew that this was more or less what was going on. And so you will find an interesting discussion bubbling along just below the surface now about the possibility that someday the executives of the companies that were involved in climate change may be in a similar position that the tobacco companies were. I'm not a lawyer. I have no, but it is fairly clear that some companies that have been associated with efforts to not give you this talk had really good scientists, and the science on this is good enough that at some level they knew that you burn fossil fuels, that makes CO2, and CO2 is radiatively active, and that matters, and we interact with the climate. Yes?
As far as social action goes, do you support divestment from fossil fuels as a strategy to kind of start the movement away from
Okay. So the question, if you did not hear, was do I support divestment of fossil fuels as a way to move? I'm going to do something that you're not going to be happy with, which is I'm going to duck and weave. When I'm speaking from the position of a scientist bringing you the information, I personally try very, very hard not to advocate for any particular policy, whatever it is. And I will more than happily chat with you offline. And I vote, I have opinions, I'm a real person and no one can get away with it. The National Academy, when they have people serve on committees, if you have taken strong positions publicly on policies, that does not disqualify you from serving. But you have to be very upfront about it, and it causes a little shadow because people who have taken strong positions publicly on something tend often to have troubles to walk away from those. And so but when you go out to what do you do? Right? then it's a very different story. And what I normally tell people who want to say, what should I do as a person? I say, first of all, do the big thing. So this is voting, this is communications, this is, take what you know and what you believe in and use it. And that includes voting. And it includes talking to your neighbors, and it includes other things. And then I generally say, pick something that you think will work, that works for you. And do it, because not only will it make you feel better, and it will make a little difference, but it's part of the procedure of building capability. It's, if one person rides a bike, it doesn't change the world. I ride my bike a lot. But if a whole bunch of people ride bikes, pretty soon somebody builds a bike trail, and then the world changed a little bit. And one person putting solar on the roof may not make a difference, but if a whole bunch of them do, it might cause somebody to say, well, maybe we need to get the electric grid so it knows how to deal with this. And it might help it so that the roofer comes to fix your roof after the shingles blow off, says, do you want me to put the solar on there as long as I'm up there? And then the world has changed. So capacity building, doing something that helps, that you were good with, is part of something that can grow. Yes? Sorry.
At the beginning, sorry, but you mentioned the transition from hunter-gatherer to historically agriculture as perhaps being caused by increased population. I was going to elaborate a little bit, and what other solutions there were that kind of increased that change.
Right, so the question of whether this transition to agriculture was forced by lack of food, you will find people that say, well, you couldn't do the transition until times were really good, so they did it because things were really great. You will find economists who say, well, as an agrarian, you're opening more jobs, you're opening more niches, there's more things that you can do, and so therefore you did it because it helps the economy ultimately. And so the job of running around picking lice off of your neighbor was already taken, but the job of striking the dirt with a stick wasn't, so there's more jobs. And so in some sense, that one is actually the same as mine, but it's a very abstract sense, but it will turn back into it. And we can't prove this, right? So I walked you through the initial story, and I can't prove to you the world was full, but we do know with very high confidence that as our ancestors swept across many places, they were accompanied by a wave of extinction of large things. And the moment that a fluted point spear showed up in the ribs of a mammoth, we lost most of the mammoths, except on a couple little islands where there weren't people. And then the mammoths lived thousands of years longer. You'll hear somebody say, oh, they were killed off by the climate change, but the climate changed on those little islands where the people weren't and the mammoths didn't die. Right? So it's fairly clear that we were bumping up against things. And it's virtually unequivocal. I will virtually guarantee you, you go out in any direction from here, or in any direction from my house, and look at how much is available to be eaten as you walk through it. And how many people could you support? And you will come up with a number which is very much smaller than the number of people now live here. And I don't think there's anyone would have any serious discussion about that.
All right, with that, I think we need to end. There's a reception in the breezeway just outside. I'd like to thank Richard again. So following up on this, he has a book called Earth the Operator's Manual. Highly recommend it. There's also a very good PBS, is it 1 episode?
3 hours.
3? Oh, so all 3 got finished now.
Yes.
So check that out. And Richard also has a book called 2 Mile Time Machine, which actually talks a bit about the paleoclimate record he was showing early on and was one of my major reasons why I'm a geologist today. So with that,